Good morning, everyone. My name is Beth Capellas, and I am the Marketing Manager here at Triangle Microworks. I'd like to welcome everyone to our latest webinar, a holistic approach to facilitate the IEC 62850 process. This is a two-part webinar series. We will be covering part one today, specifically IEC 62850 specification and design. We're expecting a very large crowd this morning, so I'll go over some housekeeping items while everyone is still joining. The webinar is scheduled to be about an hour long. However, we typically get a large amount of questions, so we are happy to stay on longer to answer as many questions as possible. With that said, I'd like to encourage questions throughout the webinar. Since the audience is on mute, go ahead and submit your questions using the webinar menu under the section titled Questions. You can start typing them in as soon as you have them. Don't feel like you have to wait to the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We will also stop a couple times throughout the webinar to read and answer questions. And then, of course, there'll be some time at the end dedicated just to questions and answers. With that said, I'd like to introduce our speakers. First, we've got Joel Green from Triangle Microworks. Joel has worked with communication protocols for over 15 years, with the last 6 years in the power industry. He's the lead engineer for our IEC 62850 development and products at Triangle Microworks and is heavily involved with 62850 industry groups. He also works as the co-editor of IEC 62850 7-2. He is a member of the UCA Test Committee and Test Procedure Working Group and involved in the IEEE Standards Association. We also have with us Christoph Brunner, who is a utility industry professional and expert for over 30 years. He is the president of IT for Power in Switzerland and the organizer of working groups responsible for the core parts of the IEC 62850 specification. With that, I'd like to go ahead and hand it over to Joel to get started.
Thanks, Beth. Good morning, everyone. Good afternoon, wherever you are in the world. I'm going to start with a quick overview of Triangle Microworks, who we are, what we do in general. Then we're going to move on to talking about the engineering process. Triangle Microworks has been around since 1994. We're located in Raleigh, North Carolina, and we have customers all over the world, more than 70 customers. Our core business is source code libraries, which help equipment manufacturers develop devices without having to specialize in the various protocols. We also build tools on top of those that are a lot of help to electric utilities and system integrators. Our products are based on international standards. Beth mentioned a number of the groups we work with. Triangle believes in supporting these efforts and giving back to these groups to maintain these standards so that they continue to meet users' needs. We're very involved with the IEC for 61850. The UCA International Users Group maintains the conformance test procedures for 61850. We're also very heavily involved in DNP, which is now an IEEE standard, as well as Modbus and OPC. Being involved in these groups directly let us feedback and help our customers meet their needs. So a brief overview of our protocols. As I mentioned, our core business is source code libraries. We write the stacks that implement these standards and protocols. On top of that, we build a number of simulation and testing tools. We'll see how those stack up here in a moment. And we have a protocol gateway product that allows you to translate data between any of these systems. Our 61850 product line, we packaged into a convenient toolkit. It includes the three major products. SCL Navigator we'll look at today. Two other products we have that we'll look at in a later webinar. Test Suite Pro is our diagnostic client and diagnostic test tool. And Distributed Test Manager is primarily our simulator designed for helping test out system configurations. 61850 brings a lot of concepts to the design of power systems that are additional to what previous wireline protocols have brought. Some of that is the semantic data model, a very important piece of the pie that allows us to communicate what the data is in the devices in addition to the raw numbers. but it also standardizes the design process. And that's what we're going to talk about today. The design process is based around system configuration language, which allows tools and devices from different vendors to exchange information. And this is an overview of the whole process and how Triangle tools can help you be successful in these implementations. On the top line here is generally what we're going to cover in today's webinar. We start with the devices. Every device manufacturer selling a 61850 server needs to provide a file called an IED capabilities description file, which describes the data model and the services that that device provides. We'll see in a few minutes how our SCL Navigator helps those vendors produce that file. That file and the others for the other devices in the system go into a system configuration tool. Triangle is partnered with Helix. Helix STS is the premier vendor independent system configuration tool. So we're happy to partner with them to do this piece. We'll see a bit of that a little bit later. Christoph's going to show us how that system configuration is done. Well, then when that system configuration file, the SCD, is produced, it is then consumed by the IED configuration tools for each of the different vendors. And this is a place where we can get into some troubles in the field. Unfortunately, there's sometimes disagreements in how the standard's interpreted, how SCL is consumed and produced. And so we see a lot of customers that have a lot of time and expense wasted in the field when the SCL file is transferred between two tools and the vendors disagree on some concept in the standard and how it's implemented, and that can cause a lot of wasted time. So we found it's very valuable to have a third party and independent tool that can verify that SCL file against the standard, not only with a schema check, but a model check and validate against a lot of other details in the standard to make sure things are right. And that's another key role of the SCL Navigator, is to verify those files are completely correct before you get into integrating them. Down here in this diagram, this section we'll be looking at in the next webinar. As I mentioned, our Test Suite Pro tool allows you to help verify this, and the DTM simulates it. So as you've got this design together from the SCD, we can simulate that in DTM, test the system configuration with Test Suite Pro, and then move on down into implementing it with the real devices as those become available. So that in a nutshell is the 61850 engineering process. Christoph's going to give us an overview of the system we're going to be looking at today in just a moment. Beth, do we have any other questions before that?
We don't have any questions to start with, so I will go ahead and switch it over to Christoph. Christoph, I'm changing into presenter. You should now have control.
Yes, thank you, Beth, and welcome everybody as well from my side. Okay, so today, as Joel mentioned, we will look into the different steps for a specification and design of a system. And in the June webinar, we will show you how to test the design that we made today using simulation and various tools. But before we start with the design, I would like to introduce you to our little application. Okay, so this slide shows the substation that we are building today together. We have a high voltage substation with two line bays, a measurement bay, a transformer bay, and a bus bar. Before we go into the steps of the specification, I would also like to, the functionality that we have to do. So this slide gives an overview on the different functions that we assume for our use case. Line protection with different elements, reclosing, synchro check and breaker failure, transformer and bus bar protection, bay controller with control interface to all the switches and breakers, measurements, and also receiving the trip from the bay controllers. As a reminder, on 61850, In 61850, functions or functional elements are represented by what we call logical nodes. And here we have a few of these logical nodes that we will use in our example today. The logical node for the trip logic, the PTRC, the recloser, switch control, XCBR. This is just a few examples. And as you will see, it's mainly with these logical nodes that we specify the required functionality when we do the specification. We will create SCL files, system configuration language, as defined by 61850. An SCL file consists of multiple parts. We have the substation section that describes the functionality. That's the part we see up here. We have for each of the ID, we will have an element in, and we have one element in the design or in the specification and design, which is the communication part that describes how the system is configured. Okay, with that, let's now get into the specification stage, where we use the Helix STS as a specification tool, and we produce the variant called System Specification Description File, SSD, a variant of the SCL files defined in the standard. During this phase, we are mainly filling in this first part of the SCL file, which describes the substation section or the functional part of the system. The specification can be split in three parts. First part, we do the one-line diagram with the process hierarchy, the substation topology. Then we do the functional requirements. We create functions and we specify logical nodes as functional elements that we require. And last, optional, we can also allocate functions to virtual IDs. With that, we can express how our system should be structured and implemented with various IDs. The slide here is the initial screen when you start up the Helix STS tool. It offers you a couple of tools that you have, and in the first step we will now use the single line tool that allows us to create a single line diagram. When you open, you have an empty screen with a palette with various equipment, and then we can create our substation. We call them New Orleans here. We can create our voltage level. We call it D1. We then can add a bay, call it line 1, and then we can add the conducting equipment that we use in our bay, like circuit breakers, disconnecting switches, voltage transformer, current transformers, and the line. And at the end, we need to connect everything electrically, and with that, we have drawn the single line diagram of our bay. The next step, we have to add the bus bar. We connect it as well to the bus bar. So that's in a very fast overview the way how the one-line diagram is drawn. And if we now want to see what we already have produced, we select from the tool export a file. We include a substation section. We export an SSD file. And then our tool provides us a little navigation window where we can open. We have seen the file that here has been created. We can open it either with an SCL model editor, which shows us now the model that we have created as a hierarchy. All these models are hierarchical. We have the substation that we created, the voltage level, the bay. We have the various conducting equipment like circuit breakers, like switches. So we have the various conducting equipment. So that's the model view, but we also can look at the same in what we call an XML view. So here you see the XML file that has been created in this first step. So with that, the one-line diagram is defined. We also have with the terminals and connectivity nodes, we also define the connectivity. The next step is to define the functional requirements. And as mentioned, we create functions and then we add logical nodes. The functional requirements we define with a function editor that we can open by double-clicking on the bay. And then we get a view like the following, where we have our conducting equipment. And what we see, the tool automatically, while we created the single line, already created a series of logical nodes and functions that are related to the conducting equipment. As an example, For the circuit breaker, it created a logical node XCBR, the switch control, and the interlocking function. But of course, we need to add more functions, and for that, the tools provides us the possibility to create a new function. We can call it QC1 control, or we can have an ASIC function with measurement, and then we can add logical nodes into this function, and with that way, basically, we define our functional requirements expressed in logical nodes. The last step of the specification is the option to allocate now the functions to virtual IDs. And this is shown here. So the tool allows us to create a virtual ID. We can give him a name as a role, and we then can associate functions that we have. We can assign them to the virtual ID. So in that case, all these 4 functions have been assigned to the bay control unit. The result of our application that I introduced in the beginning for one bay is presented here. So we have the bay control unit that implements the measurement function, the control of the 3 switches. We have switch control unit that implements the interfaces to the 3 switches. So we assume a fully digital substation with merging units and switch control units. We have the merging units implementing the voltage and current transformers. And we have our protection device with all the protection functions, the reclosing function, the synchro check, and the breaker failure function. And if we blend this in our hierarchical overview, we see here now a few of the elements. We see the voltage level. On top, we see the measurement function with the logical node measurement unit as part of that function. We see breaker control with the switch control and the interlocking logical node. We see the protection function that we created with a differential element, 2 distance element, the distance, the scheme logic, and the trip logic. We also see as an example down here the conducting equipment of the breaker with the logical node XCBR being the breaker interface. And we also see a conducting equipment transformer with sub-equipment per phase. And here we see a logical node TCTR representing the interface of the phase A. And with that, we have created our specification. And I hand back to Bess if there are any questions before Joel will continue and create the IED specific SCL file.
We do have a couple of questions that have come in. Let me go ahead and read the first one. How logical node XCBR represents all the properties of breakers if only 2 on-off status and commands are connected to the IED?
Can you repeat if only 2 on-off status? Well, the logical node XCBR basically can represent as much as is wired to the IED. The minimum is typically the position, so the contacts for open and for closed that are wired. But in many cases, you may want to wire additional information like an operating capability that a breaker has, depending on its mechanical charging, how many open close cycles can be done. If this is wired as well to the IED, we can represent it. If only the position is wired, this is the minimum information that we then represent.
Okay, and I do have another question for you, Christoph. Why there are a need of 2 separate logical nodes for breakers, for example, XCBR and CSWI?
Okay, the XCBR, as mentioned, is representing the interface. So that's the pure image of the contacts that you would get in a conventional system from the breaker. The CSWI is the control function as such. So that's the logic, the software that is performing, as an example, interlocking check to figure out if it's allowed to operate a breaker, that is probably performing synchro check, if we need a synchro check. So that's really the software function that is executing the control. The XCBR is purely representing the interface signals.
Okay, and I think we'll do one more question before we hand it back over to Joel. What is the application of this virtual device?
The virtual device is useful as an add-on to the specification. With that, the user can express the requirements, which functions he wants to have implemented in what device. Sometimes you may have constraints that you want, as an example, do the reclosing in the protection, or you want to do in a bay controller. So with that, you can express which functions will be realized by what kind of devices. So if you want to go to that level, that's an option. We will see in the next step when we do the system design, this also helps then to easily continue with design by mapping then the virtual IDs to the real IDs. But that we will see in the third part of this presentation.
Okay, and with that, Joel, actually I have a question for you. It's going to segue into your next section of the presentation. Is there any tool available which can compare the two different versions of CID files?
Yes, there is, and we're actually going to get back to that in my next section in a few minutes. We'll talk about how to compare those files after we put together the system file. That's all right.
Okay. Yeah,
All right.
and with that, Joel, you can take it.
Thanks, Beth. So we're going to go through, as I mentioned in the introduction, sort of the starting point, the lowest part of all this. We've got devices in the field that build up models to communicate data from the servers. Takes a number of those to build a system. So we're going to show how a device vendor is going to build up that ID capabilities description file for one of the bay controllers that we're going to use here. This is Triangle's SCL Navigator product. The first use case of this is to build this ICD file. So we'll start here, and we're going to build a new file. And in this case, we're going to build a edition 2 file, which is the common point in the market right now. Edition 2.1, the first amendment to this, has just been released. We'll start to see those devices shortly, but we're going to go ahead with edition 2. And so I've got to give it a file name. And then we've got a little dialog here that lets me set some basic information for the file. We've got an identifier that's a token, text string, vendor information, and version number. In 61850, analog values can be represented either as a floating point number or as an integer with a scale value configuration to go along with it. There's a couple cases where the integer representation is useful. First of all, there are small devices, processors that don't do floating point math. Those can be represented this way. Sample values oftentimes uses an integer representation to meet performance needs. But other than those cases, we generally want to use a float. If we put both in the model, the server has to keep the data consistent, and that's usually not worthwhile. So this is going to set the default in this file to use floating point numbers. We can override that at any level, but that keeps us from having to make that decision most of the time here. So with that, we're presented with a basic template to start our device with. We've got the IED level, server level, the logical device level, and a server has to have a logical device, and a logical device has some information about the device itself presented in LLN0, so that always has to be there. And the LLPHD logical node gives us the physical description of the IED itself, so we have one of those in an IED. So these are all the requirements that any server has to start with that we pre-populate here. And then to build out our bay controller, we need to add the other parts of the data model. So what we provide in this tool is this LN library here. If I click that, I get a toolbar on the left-hand side that shows me the logical nodes from the various parts of the standard. The ones we're using today come out of 7.4. We've got a couple other standards here, some DER, and some technical reports that provide some additional logical nodes, but we're sticking with 7.1 today. Interesting question came up there at the last break about modeling a circuit breaker. It's true that we need an XCBR and a CSWI to model a circuit breaker. And that's what's going on in our bay controller here. So we're going to add those. So I open up my C group, and the logical nodes are grouped by the first letter, and C is my control group. So there's my C switch. And I just take that and drag it over here and drop it on my logical device. Now this panel in the middle I just dropped it on is a navigation pane, and it allows me to jump to any logical node in the file quickly and easily. One of the features we add here to help you find your way around the file is why the product's called Navigator. So when I drop that on the logical device, I get this logical node editor window that comes up. Now I don't have any CSWIs in this model yet, so my only option here is to define one. If I already had one, I could use a duplicate of that template and keep going, but I don't, so we have to define our first one. For every logical node, we have a prefix, which is a text string defined by the system designer. In this case, we're using QA1, not QA exclamation, to indicate the line that this breaker is attached to. The instance value is added to the end of the logical node name. The Navigator tracks that for us automatically. We can override it if we need to, but generally manages that. So if I click next, then I get a list of all the data objects that are available in this logical node. And the mandatory ones, according to the standard, like here, the behavior, are pre-selected for us. So we don't have to worry about that. But let's go through here and see if there's anything else I need in this model. In a control, 61850 provides some testing functionality, test modes and blocking modes. And those can only be activated if I have the mod control in the model, which ends up setting the behavior. But to control it at this level, I need the mod, so we'll add that. And we can add some nrefs here so I can track where some of my inputs are coming from. We have some other fields here. Our local mode, we're not going to put this time. Sometimes that's necessary. This is a three-phase breaker, so I have the one position. It's a mandatory device. We're not going to add the separate three-phase positions in this case. We just got the one, but we could put those here. So that's what we need for this model. I need to go back up to my mod though, because by default, an ENC here shows up as status only. Status only means a control that can't be controlled, so that doesn't help me very much. If I go into this column, this shows me the type template of the CDC, the data object, is a common data class that's built from. I can select that, and I get the next level of menu, just like I did at the logical node level. I can come in here and select the data attributes that make up this data object. In this case, I can select any of the ones that have already been defined in this file. This is the default that I started with. I can select this one, or I can come in here and create an entirely new one. And we just give it some name. And here I can select the control model. 61850 has 4 control models in addition to the status only. For ones like mode, where it's an internal function, I'm not turning anybody's lights off, it's relatively safe. Direct with normal is a reasonable choice for that. So I can come down in here and add any of these attributes if I like. It's already selected not only the mandatory ones, but the ones that are appropriate based on the control type I selected. But if I want to come down in here, I can add my opera timeout. It's always a good thing to do. I don't need an SPO timeout because I've gone with direct control. I can put in some of my op status information, be able to track what's happening in this thing. And I gave it a new name. So that's all good there. I finished that. And now my mod has the CDC type that I just created. So there I'm finished with my LN. There's my CSWI, came up there. And as the caller pointed out, we also need an XCBR down here in the X group. to model both sides of the functionality of this device. Again, I just drag it to my logical device. I give it the same prefix here so that we know that it's the same device on the same line. And I go through the same process to decide what I want in this device. So I can go back in here as well and set the mode in this logical node. And I want my mode to be controllable. Since I already defined how that's going to work, I can simply select the template that I defined last time. And now I can reuse that, which is, of course, a goal of 61850 to be able to reuse designs and reduce engineering work. So otherwise, this guy is what I need for this model. So now I've got my breaker modeled, both the XCBR and the CSWI. I'm going to go look through here. From here on out, it's really repeated that process to add the other logical nodes. So we're just going to go through a couple other features of the tool here. SCL is built up of data type templates. So again, we get a lot of reuse of design. The navigator gives me some features here to allow me to move up and down this model and find out what I need. So at any point, I can come in here and select navigate to. In this case, I get navigate to template. And I can come down here and I can expand my logical node type, and it shows me all my DO types. And from there, I can also navigate to my template and see what that DO looks like. And I can expand that out. And from each of these, I can look at all my siblings. I can add data that I'm missing here, and I can come back up and navigate to the usage at each of these DO types. So as I go back up, again, reuse of design, we're reusing these templates. So if I think I need to change this thing, I can easily see every place that it's going to be affected in my model. So I'm going to come back up. I'm going to come back up to my usage here and get back up to the top. So in these, we've just got the one line representing the LN, points to the data type templates. I can build that all up. Well, sometimes I need some instance data described in my SCL file to tell me details of what this unit is. And that requires building out that whole structure from the data type templates into DOIs and DAIs. Very tedious to do in a text editor. So what I can do here in Navigator is I come in here and right click and I say add instance data. And that builds out the whole tree for me automatically. As mentioned, I've got tools in here to expand and collapse things at the various levels for where I need to be. So I'm going to expand all my children. So with one click, I just added all this instance data so that I can come in here and add the information I need into here. So if I come down and look at my position, I've got an ST val in my position. And one of the things that we often need on a status value or measure and is an S address, a short address, which is a token that my software in my server can use to identify a location in the device itself, actually. So I'm going to come in here and I can give it, this is an arbitrary string that only my server has to understand, so I can put whatever I want to in there. Just made up that name. All right, that's all I need in here for now. So I come back up, and again, with one click, I delete unused instance data. And it gets rid of everything that's not necessary there. It's important in SCL to collapse these files as much as possible. They can get very large, so we need to minimize the size of the file everywhere we can. Along that line, some of these data type templates end up getting duplicated, particularly at the later stages when you're merging devices into a system configuration file. So we have a tool to clean all those up. It automatically compares the templates and finds duplicates and removes those. So we've got a nice tool there for that. then when we're trying to visualize what this model looks like online, it's very difficult to do from the SCL because of the way the templates are constructed. So we have a model view tool here. And with that, I can quickly build out this whole device and see what this tree looks like online as a client would see it in the server. Again, we have a navigation pane to help me jump to the pieces I need in here. And I can quickly visualize what's going on in the device. So that's how we build out an ICD file. As I mentioned, just a few more clicks to repeat dragging logical nodes and set those up here. And I end up with this file. This is my basic Bay controller, which I'm going to hand off to Christoph as he gets back into the system configuration section after we see if Beth has any questions.
Yep, we've got a lot of questions coming in. So let me just grab a couple of them. First one, what's the usage of the prefix field defined in the logical nodes tags?
The prefix field is a fairly arbitrary string. Of course, there are limits on the length of it and the character set that's used, but it's used by the designer to indicate what part of the power system that LN is attached to. It's a token.
Okay. Can we convert SLD to SCL files automatically using any of your tools or source code?
SLD files are not in a standard format. Maybe Christoph, if you want to jump in here, but so it's very difficult to convert those because there's not a standardized format. They're a drawing basically, but there's a lot of work to try to ease that process. Christoph or Jörg, if you want to add anything to that.
No, as you said, usually there is no standard format for the way how you draw your single line diagram if you're not using a standard tool like a 650 tool like I have shown before. So if you have a single line drawing from AutoCAD or whatever, it's not that straightforward to convert to it.
Okay, next question. How many RCBs can be created in one IED?
That's a function of the device itself. In the ICD file that I just presented, there's a services section. I believe I'm still showing my screen back.
Yes.
So in the services section here, the conf report control, the IED vendor has to specify based on the resources, memory essentially available in the device, how many it can support. That's purely a function of the device itself.
Okay, let me give you one more, then we'll switch back over to Christoph. Usage of prefix and SCL file, is that required or optional?
I'm sorry, is an SCL file required?
Is usage of prefixes in an SCL file required or optional?
It's required.
Well, the LM prefix is optional, but when you need them, when you have multiple ones, you need to put them.
Yeah, I was about to backtrack there. According to the schema and the standard, it's not strictly mandatory, but I think it would the system would get confusing in a hurry without them. You agree with that, Christoph?
Well, I mean, I didn't put a prefix for the MMXU before, or for the reclaw. Yeah, for the MMXU, I didn't put one because it
depends on how many
design.
you have.
Okay, and with that, Christoph, I've given you the controls back again, if you want to continue on.
Yes, so welcome back. I hope you see the screen again. So now that we have done the specification, we also have the ID files, the ICD files. Now we can go into the system design. So the system design, what we are doing here, we import the file that we created with the specification. We import the ICD file that Joel created, as well as other ICD files for protection for all the devices we need. We import that in the system configuration tool, and then we do the complete design and create at the end what we call the SCD file, the system configuration description file. So what is done from the specification that we import, we have our substation section in our SCL file. From the ICD that we import, we create as many instances as we need that device in our system. So if we have 2 feeders, we need the bake controller for the feeder twice. So we create 2 instances of that. And during the design of the system, we also populate the communication section with all the information related to the networking, like IP addresses. So this is an overview on the different steps we have to do. We first have to define our protection and control schemes, the signal flow that we need for our protection and control schemes. We then have to create the aspect of the system diagram, the communication network, the ID instances with the connections to the network and the communication parameters. Then we have to implement our functions, which basically means we have to map the logical nodes from the specification that we created onto the logical nodes in the IDs that we have in our system. So we need to say which ID is the interface to the breaker on line 1, which ID provides the interface to the breaker on the line 2, and which switch logical node is the interface of the line disconnector, and which one is the interface of the bus bar disconnector. So all that needs to be specified. And then at the end, we have to finalize the communication, which means we have to design signal flow for reporting, and we also have to create control blocks. So the first step, define schemes, and we are still using the Helix STS tool for that. The first thing before we can start drawing a protection or control scheme, we need to configure signals. So we need to identify what signals are we needing. So we can right click on a logical node, we can select configure signals, and then we get the list of all the available 6150 objects, and then we can add those that we need for our application, so that we don't need to select always from the whole set of signals. We can more or less add what is required for our applications. We then do our application design, and that's another tool in the Helix STS, which is called applications. And in that tool, we can create a scheme, an application in the same way like you would do in a conventional system, a drawing of wires between the devices. The only difference is now we are drawing virtual wires between the different functions. So the first thing is we create a new Goose application, and as a result, we can do that. We can then open the application editor, and we can create the application control for the line 1. Once you have created the application, now we need to select the functions that are participating. We can start selecting a sending function. When we select from the palette sending function, we get a list of all our functions that we have in our specification, in our design. We can select them, and we can add them to the drawing panel. So now we have selected here a sending function, which was the QA1 control. We also have selected a receiving function, which was the breaker interface. And now we can select from the sending function signals, and we get the list of all the signals that are available from that function. And in our case, we select the operate open and the operate close as the 2 signals that need to be sent over to the breaker interface as the receiving function. So we basically wire the sending function to receiving function, and we have a wire for each of the signals, which is 6150 data objects that are sent, and we can indicate to which logical node in the receiving function this signal has to go. This picture shows now the overview of our design again, what we need to do for the control. So we have the breaker interface with the breaker logical node that receives the operate open and operate close from the switch control. It also receives a retrip, the opt-in from the breaker failure function. It receives the trip from the protection function. The synchro check sends a release to the control function. So the function can both be a sending function, but it can also be a receiving function. The reclosing sends a reclose request to the control function, and the switch position is sent to all those various functions that are interested in the switch position. And with that, we have designed our application. There is not yet anything with 61850 except the signals. We will see later on how out of that goose control blocks will be created. But first, we need to create our devices. So we need to do the system diagram. And for that, we import now, we import files, and in this case, we import the ICD file. So the ICD file that Joel has created will now be imported. And then on the system diagram, we can place the device. We can give it a name. With that, we create an instance. So we have selected the device from the palette, have dragged it over here. We have then selected a name to give it a unique name. We then connect it with the connect to subnet. We connect it to a subnet that we have created, represented here by a switch, and we also assign an IP address. At the end of that step, we have our system diagram with an HMI, with a protection unit, the switch control unit, a bay control unit, all then connected to the same network with various IP addresses. Now that we have all the devices in the system, we go to the next step. And now we have to link or connect our devices to our specification that we made earlier. As we made virtual IDs, we can do that in two steps. We can first map the device to the virtual ID, the real device, and then we have to map the logical nodes. So the first thing from our specification, we can right-click again here on our virtual device that we call bay control unit. We say we want to implement that, and then when we select implement, we get a list of the devices that are in our system that we created before, the real devices. And in that case, we say we want to implement that with line 1 bay controller. And if we click OK, we then have now not anymore an indication virtual. Now we have here the name of the device that we have selected, and here we have the type of the ID that was in the ICD file. And we see with the symbol here that this device is now implemented. This virtual device is implemented. So that's the first step. The next step now, we need to tell which logical nodes. This device may have many logical nodes. We need to tell which ones to use to implement our specification. We see here this chain symbol, which is not yet closed. That means those logical nodes from the specification didn't yet find a corresponding logical node in the BCU. And for that, we double-click on this symbol to open another editor that allows us to map functions. So we can select down here. This gives us the list of all the logical nodes that are defined in the ID. We see there is an MMXU, and by clicking there, we can say this MMXU shall be used to implement what from our specification. And with that, we can map all the logical nodes we require. And at the end, when we click OK, we will get all these symbols linked. So here we see all the different logical nodes from the IDs and what we use them in our design, what functionality, what logical node they realize from the specification. And at the end, we see all the logical nodes linked. So this is an overview now. Everything has been implemented. All the logical nodes have been linked, except one here that is not yet linked. And what we also can see in some cases, when somebody is not linked correctly, it indicates us if there is some problems. Once everything is linked, we have to finalize our design. The first thing we need to do is to define the signal flow for reporting. So the MMS-based reports that are sent, as an example, to the HMI. This we can do in a function editor on the substation layer level, that when we double click here, we get a function editor where we can place a virtual HMI, where we can add an HMI function with a logical node IHMI. We can map that then to our HMI, and then we can select here on this logical node MMS reporting inputs, and this gives us the possibility to select from all data objects and data attributes available in our system which ones we want to use to report to the HMI. And then we click OK, and the last step is fully automatic in this tool. It's the magic button that we can select, which sets the communication settings from specification. We can select if we want to configure all IDs, all report goose sampled values. So it's taking the specifications we made for the schemes with the wires that we connected between the sending and the receiving function. It considers the inputs that we configured to the HMI, and then it generates automatically all the control blocks we need. And we can verify that in the communication editor, which is another tool. And then we see, as an example here, the ID created a goose control block here in the bay controller with those signals that are put in the goose message. It created another goose control block in the switch control unit. We also see here who is the receiver of the signals. We also configure the XREF that is needed, so everything is configured automatically in the background. And with that, the system design has been made. The STD file can be exported, and Joel will then verify if everything was taken over correctly from the ICD file or not. And with that, I hand back to Beth if there are any questions.
We have lots of questions coming in. So I will go over just one or two of them because we are running short on time. But as I mentioned earlier, we will stay on after the webinar is over to answer as many questions and answers as possible. As long as everyone wants to stay on, they can definitely hang on. Okay, so Christoph, will you be able to import vendor-specific ICD files when adding IEDs to a system diagram?
The import, in fact, is done before, and I probably can move back. The import is done in the workspace of the tool. And once I have imported the IEDs, I see all the vendor-specific IEDs down here listed. And then I can simply drag them over, and with that, I create an instance of them. Okay.
Okay. How will we come to know what IP address is assigned to which device?
Again, that's done when I connect the device to a subnetwork. I can define the IP address. We see here on the next slide, I think we see multiple ones. So each of these connections here has as a property an IP address, which is the IP address that the IED is connected to that subnet. An IED may have multiple communication ports, and it can be connected to different subnets. Then for each of the subnet, we will provide an IP address as we want to use it. Okay.
Okay, and for the sake of time, I'm going to switch back over to Joel, and then we can circle back to the other questions as they're coming in. Okay, Joel, you should have control again.
Thanks, Beth. So let's go look and see if Christoph has done a good job here. As I mentioned in the overview, the second use case for the SCL Navigator tool is to verify SCL files at every point in the engineering process as they're transferred from one tool to another, so we can catch any critical bugs at that point when it's cheaper and easier. So we've loaded the SCD file that Christoph built with the Helix product. At this point, we've got to collapse down to where we're seeing the IED names. Again, we've got the navigation panel over here, so we can jump into whatever point of the file we want. What we're looking at the moment is our Verify tool. We're going to come up here and we're going to run SCL Verify. And this is going to produce us a list of any issues in the file. It starts with a schema validation, which is an XML schema. SCL defines. That's good for token validation, input validation, so forth. The syntax of the file, not nearly enough to see if the file is useful, but it's a first cut. So we've got a schema validation error here. So if we jump down into this, we get the line number where we find the problem, and a click will get us right to it. And this is telling me that I need a log name. And so if I look down here, the editor gives us all the ideas, and here in orange is log name, and it's orange because we're required. And I should have a log right here. So I'm going to find out in a moment that I'm missing a log, so I can go in here. And we're cheating a little bit here. This is an SCD file. We can't really change device properties here, but if we have to get a job done today, we can come put the fix in and tell the folks at the other point in the process what needs to be done to make it work. So I'm going to come into my own 0, and I'm going to add a log. And his name is generally going to be the L device name, but we're just going to give it a simple name here. And then I can come back to my log control and add that name and save my file. And this is a history item dialog that's going to try to encourage me to do the right thing and put a revision note in the file. As soon as I save the file, it reruns the verifier for me automatically, and that schema error has gone away. The next section here is called information. These are not warnings. These are things Triangle's decided are helpful for you to know about the file. And so we provide a lot of statistics and background information here. There's 9 servers and 1 client defined in the file. You built this file. Hopefully those are what you're expecting to find. We talk about how many GGIOs are here because, well, that's really not the right way to do things. So we want to give a little information. And we go through each logical device and provide a good bit of statistics of what's going on in each device. Now we get through the information section, and we can collapse all this in the tree to organize what we want to see, and we can sort by it up here. So we've got a set of warnings down in here. And what this is telling us is that we've got settings controls in a number of these devices, but there aren't any attributes in the device assigned to a setting group. And it's not wrong. The device has this capability. We didn't use it. That's okay, but it's worth noting so your engineer can go back and look at it and make sure it's what it should be, because it's not quite right, but not really wrong. So it looks like overall, Christoph's done a fine job here, and we've got a file that should work very well. So the other critical component in comparing an SCD file is we want to make sure that we've got the files, the input files we expect to have in the final file. As I mentioned in the fixing that log, we should have sent that back to the device vendor, have that corrected in the device configuration, and gone back through what's called the round trip engineering process. And if those ICD files are updated as we're working through this, well, we want to make sure we have the final version of each of those in the final version of the SCD file. So to enable to do that, as well as the question in the first break about comparing ICD files, we have a tool here called Model Compare that accomplishes both of those functions. And we can compare essentially any 2 SCL files. Now, of course, if the SCL files are not in any way related to each other, you're not going to get any useful information. But if the models are somewhat related, we can determine if there's any differences and describe any differences in the two. So here we've got our SCD file that we just came out of the system with. And here we have that ICD file for the Bay controller that we started with. This tab tells us communication sections. This ICD file is a template file, so it doesn't have any communications information. So we're expecting all that to be showing errors. In the object model view, we can come in here and pick any of these we want to compare to. Now this is the template for the Bay controller, so it only makes sense to compare these two Bay controller files. We'll pick one of those and we'll look through that. And here we can expand this out and see the whole tree where there are problems or where there are things that look okay. And over here on the right, we have a report of just the differences. And what we see here are largely things we expect to see. LGOS logical nodes are reporting information on Goose subscriptions, and those get instantiated in the system configuration tool. So we don't expect to find those in the ICD file. That's fine. Our control blocks get instantiated at system configuration level. Again, we don't expect to find any of these things in the ICD file. So everything looks very good there. That quickly lets us show the difference, show that this file is using the version of the ICD file that we expect. And in a similar way, we could compare those two CID files that the caller asked about earlier. So that's the gist of how to check your files and see that they're correct and what you're expecting as you move through the engineering process. Beth, do you want to go back and see if we have any other questions at this point?
We do have quite a few questions. However, we are at time. So what I would suggest is let's just to do a quick wrap up, and then we certainly are going to leave the line open and we'll stay on as long as someone wants to stay on with us to go through all the questions we have here. So with that, Joel, I don't know if you do want to do a quick wrap up or you want me just to go to the next part, my last part from here?
Yeah, well, I think, well, you were going to go through the questions and talk about the next webinar, I believe.
Yep. So for everyone that's not able to stay on while we keep the line open, we will be sending out additional information about the products that you've seen here today, both SCL Navigator and HeLinks. You'll also get a short survey once you sign off of this webinar. So we really appreciate anyone that can respond to the surveys. Let us know what you thought about this webinar, what information you want, additional information you want to see. And then our follow-up webinar to this will be, the date for that will probably be announced in about 2 weeks, but we are planning to have it in June. And that really is going to cover the testing and the simulation of the design of what you saw here today. So please stay tuned for more information on that upcoming webinar. And as I mentioned, it will be sometime in June. So with that, anyone, we still have a lot of people on the line. So anyone that wants to stay on, we're going to leave the line open and just start to go through the list of questions. So feel free to continue to ask questions, and we'll just keep going through them until we're done with the list. Okay, so with that, I'm just going to start with the last question that we were asked, and then Joel or Christoph, between the two of you, you guys can jump in and answer the question. How do services compare with actual IED when we create using specifications? How do we check the specification with manufacturer IED services capability? Not sure if that's a Joel or a Christoph question.
Can you read again? I didn't get
Sure,
the beginning.
It's two questions. How do services compare with actual IEDs when we create using specifications? Second question to that, how do we check the specification with manufacturer IED services capability?
Okay, so in principle, as part of the specification, we typically limit the specification to a functional specification, but of course we could also add specification of required services. So the service section that Joel has shown, where we see as an example how many reports are supported. We are currently in the working group discussing some extensions to the standards that would allow to create what we call an ISD or ID specification description file. And with that, we could express also service requirements. Currently, that's not yet directly available in the standard as such. Of course, you can use the approach of a virtual ID to do something similar. And then the tool basically will need to compare the required services against what is offered from the ID. But what the tool is doing in any case, and I think that's even more important, when the Healings tool at the end, as we have seen, is creating these automatically the report control blocks and the data sets, it is checking the service section to see what is allowed, because in some cases you may have IDs that have predefined data sets that it cannot configure, or it has predefined control blocks, and then the tool needs to adapt to that. By default, when we have fully flexible ID, the tool can just start from scratch and create those. But if there are already some there and you are limiting the way how you can modify them, then the tool needs to consider that. And then it has to do based on the service section of the device. Not sure if Jörg wants to add something or Joel.
I think you covered it pretty well. That gets to a common question, is it's a procurement question, and verifying the devices on the market provide the functionality needed. And a lot of that gets into, there's a lot of work on the basic application profiles going on to try to address those questions.
Okay, we move on to the next question. Can we do engineering of mixed edition using system specifications and do all whatever is shown today?
I would say yes, with some caveats, Christoph.
Yes, there is the part 6 of 61850 that defines the system configuration language, has an annex that defines some constraints and how mixed systems shall be working. As one condition, it is required that the system tool shall be of the highest edition. So if I have edition 1, edition 2, and edition 2.1 devices, it is assumed that the system tool supports edition 2.1. And then we have, in some cases, what we call downgrading. So the tool is able to export. So the whole design will be made on the highest edition. But when importing older files, the tool needs to upgrade these devices. Depending on the model, there may be changes. And when exporting file, it may be required that we export not only edition 2.1 file, but maybe also an edition 1 file. And that's basically supported by the tools.
Okay. All right, next question. Does the config revision for each IED come from its corresponding ICD file? And if so, every time a new ICD version is released, does this need to be updated?
Yes. However, there are several config revisions throughout the file, whose control blocks carry one to indicate if data sets have changed, but at the IED level, yes.
Yeah, the configuration revisions related, as an example, to control blocks, when the Healings tool is modifying them also, it typically increases the revision of the configuration. The model, the ID model revision, okay, if you change the ID model, there is another information, which is the revision of the model. That's, of course, when you import an ID with an updated model, you need to consider that as well. Doesn't necessarily require that you every time recreate everything, but I mean, if you have a model change in the ID, then apparently you did it because you need these additional signals. I'm not sure if the config revision was referring to those. a pure software revision that doesn't affect the model as such of an IED, that the system tool doesn't really care about.
And that would show up in the software revision information.
Yes.
Yes, not configuration.
Okay. Next question. Can you use the SCL Verify on any SCL file created from different vendors?
Yes, that's absolutely the reason for it, as I mentioned, to sort out differences in opinion between different vendors. The value of having a third-party tool to objectively identify any file against the standard. We found to be of a great value to a lot of customers.
Mm-hmm. Okay, next question. If you build the HMI logical node, where will this reside in an actual implementation? What IED?
Well, the HMI logical node in the substation section typically will reside probably at the station level. But then the HMI itself is at the end of the day also an IED in the system, like every other IED. It's probably an IED that has only a client, but it still appears in an IED section as an IED, and the HMI that is part of the specification will refer to that HMI logical node in the IED.
Okay. Do we get SCL ICD files when we buy a device, or can we download them from the device itself?
This depends on the vendor. Some vendors you can download the ICD files. That's mainly for devices that have not necessarily flexibility. If you have a multifunctional IED that you can configure with the vendor tool, whether it does what kind of protection functions it does, then you may create it with the vendor tool when you configure it to your specific purpose.
Okay.
So the vendor has to provide this file to you, but the method by which it's distributed is not defined by the standard. Some devices have FTP access directly on the device. You can get it. Some you download from the vendor's website, and as Christoph mentioned, some you produce to some extent on the flexible devices.
Okay, here's more of a generalized question. As an end client customer, we have never come across these engineering processes. Who and how these tools could be utilized, if at all we want to do this for our future projects?
One more time, please.
As an end client customer, we have never come across these engineering processes. Who and how are these tools could be used for our future projects? So basically a general question on this engineering process.
Okay.
I still didn't get the last part. Who and how can this tool what?
Yeah, who and how do we use the process for future projects?
Hello?
Yes,
Yes.
go ahead, Jörg.
So generally, utilities can use this to produce the SSD file, the system specification, which they hand over to the system integrator, which then at the end gives back the SCD, and then it can also be used to compare the results of the engineering against the specification.
Okay.
But the system integrator can be the utility itself, or a third party, or a vendor, or whatever.
Yep.
Okay, Joel, do you want to add anything, or is that it?
I did want to add, I'd like to introduce Jörg Reuter, our partner from Helix, just spoke there. I think we forgot to introduce him. Jörg's been working with the Helix STS for many years and is one of the SCL experts in 61850.
Okay, and next question. How did these tools become useful to a utility customer engineering when usually we get an SCD as an end product?
Well, I think that's exactly what, it's the same answer like Jörg provided before. I mean, if the utility customer gets the SSD file, then they will not really use the STD file, they will not really use it. They may use it to do the specification. They may use it when they later want to maintain the system. If they have contracted somebody to do the design, but later on you want to maintain it yourself, then this tool may be useful as well.
I think today a lot of utilities are really aiming to improve their purchase and specification process, so their collaboration with the suppliers. They want to more precisely specify their system in order to get similar solutions for similar substations for maintenance and also for quality. And here, the 6150 process offers the opportunity to make a formalized, standardized specification instead of Excel-based or Word-based PROSA specification document.
Okay. Is there available standard libraries from IEDs such as ABB and Siemens?
Standard libraries from IEDs. What does that mean? I mean,
Well, an answer that I have here from Jim Coates, who's online answering these questions, is the vendors usually allow downloading the latest versions of ICD files from their website or have configuration tools that allows creating an ICD file consistent with the configuration of the IED.
okay, so that would be the same question we had before. How is the IC? How do we get the ICD file?
Okay. Next question. How can it be indicated where the subscription can take place in the ICD?
Okay, there is two aspects of that. I mean, the subscription as such is configured in the SCD file. We didn't look into that in detail, but we configure the IEDs that are supposed to receive the goose message. And in the IED, we can configure with an XREF the signals that we receive on the particular logical nodes. And then there is the aspect of the live system where we have these logical node LGOS for the goose supervision that was introduced in the second edition of the standard. And there is a status indicating that the IED is currently receiving or subscribing the message. So with that, you can verify that everything is okay, that the IED really sees the message and is subscribed to it. And there we can also see when we talk about testing, but that's another topic, if it receives the simulated one or the real one. So that we can see in the logical node LGOS.
Okay. Next question. Is there a tool to test the report reservation functionality in 61850?
Test Suite Pro has features that test reporting as well as all the services in 61850. It can definitely be used to test the reservation.
Okay. Is there a way to easily merge ICD files after comparing them?
The short answer is no. We allow the comparison of those files so we can see the difference. Those need to be routed back into the engineering process and the design of the ICD file.
The merging is basically done in the system tool. I mean, if something has changed, Navigator allows us to figure out the differences, but we need to go back to the system tool to have the right file there. So the system tool, when importing an updated ICD file for an ID it has already imported earlier, it will do a merge.
I understood the question to be about doing a difference between revisions of an ICD file. Maybe I misunderstood.
Okay.
Okay. Next question. When you change only one device in Healings, what happens with the other devices? Must I update all the devices?
That depends on the consequences. If I change in one device a signal that I add to a goose control block, I probably add that because there is another one that needs that signal. So in that case, yes, I need to reload the devices that are subscribing to this goose control block. But there may be other changes that I do on a device that don't affect any other devices. So that's still the responsibility of the system designer to know what he is doing and to know if he does a change, what other IDs are affected by that change, because they somehow depend on that change.
Yeah. So if you update in Healings a communication link, then Healings proposes you to regenerate the communication configuration for every concerned ID, and indicates in a lifecycle support that you have to reload, or the set of IDs you have to reload to make this consistently happen. So you do not have to reload all the IDs, but just the IDs that have changed.
Okay. Does every vendor support configuration of IEDs via SCL, and is it mandatory?
61950 devices, yes.
Okay.
Well, they have to provide a file that represents the configuration of the device. The device can be fixed. Doesn't necessarily have to consume the ICD file.
Does Triangle have any tools to test secure MMS and Goose protocols? If yes, please explain a little bit about that.
Yes, both DTM and Test Suite Pro allow testing of secure MMS.
Okay. Will SCL Navigator verify all test conditions for ICD based on conformance?
Well, the conformance is testing at the SCL level, testing the file's correct according to the standard, which is what the Verify tool does. So I would say yes, it will verify that you're conformant.
Okay. I've got a very specific question here. Let me try to read it as accurately as possible. How do I find target points where we should place input xref and input sections in an SCD file in the IAD subscriber? I'm not sure if I'm reading those specs correctly.
Can you reread?
Yes. And you should be able to see it, Christoph, on the list of questions if you've got that out in front of you. It's the third one from the bottom.
At the bottom.
How to find target points. We should place input xrefs and input sections in SCD files in the IAD subscriber.
Okay. Where we should place input xref in SCD the ID subscriber. Okay, there is a longer answer behind that. In principle, the standard supports multiple options, and this has been clarified a lot with edition 2.1 of the standard, because edition 2 and 1 were not yet so clear there. So in principle, there's two options. One option is what we call the later binding, when the ICD file from a vendor already provides inputs that have not yet as inputs with xref, but the xref itself has not yet any binding to a source, but it already has a placeholder for an input, and the recommendation is that in the description or in the short address, we have a text that is more or less understandable for the system engineer what kind of input that is. Is it a blocking signal? Is it an initiate of a breaker failure function or whatever? In that case, the system tool, when it creates the connection, needs to connect that to the right point. If the vendor ID doesn't support the later binding, then typically in the ICD file, we don't have any inputs and xrefs. And then the system tool, according to edition 2.1, can connect it to any logical node where it needs it. So in principle, a trip signal will be connected to the XCBR. So the system tool will add an xref there. And then the IED tool needs, in the post-processing, take that and connect it to its right internal variable. That's basically the two main options as they have been now defined in 2.1. I'm not sure if Jörg wants to add on that.
No, that is fine. That is fine. That's fine.
Okay.
Okay.
So.
Yep. Next question. But the relay may not be able to support subscriptions to all data attributes. There may be limitations on type total numbers. How can all these issues be indicated to the SCT in the ICD?
I think the number can be limited in the service section. For the type, normally the relay should be able to subscribe to any type if there is a compatible logical node later on to use it. If this is not the case, then there is the option to use, as Christoph has mentioned, the later binding and not allow additional xrefs. With this, the receiver can define exactly which data and which data type he is receiving.
Okay. Can Helix monitor does Helix have a packet tracer and can monitor how fast the IEC data packets are received? And also, how big is the data being transmitted?
So Helix has no online connection. It is only for engineering, but I think there may be some tools from Triangle on this.
You're really getting more into the realm of Test Suite Pro there to monitor the online traffic. So we monitor those connections there, give some information about the traffic, which we'll go through in the next webinar, how to test those.
Yeah, so.
Okay, well with that, oh, go ahead.
No, it's okay.
I was gonna say with that, we've come to our last question. I think we've gotten through everyone's questions and answers. I really appreciate everyone that has stayed on with us for the extended amount of time. A good amount of you did stay on, so that's good to see. If you continue to have questions, please feel free to email me directly. Everyone should have my email address in the follow-up email that you get once you sign off of this webinar. Or you can also always email sales@trianglemicroworks.com. We will also be sending out a recording to this webinar, as well as posting the recording on our website, trianglemicroworks.com, and it will include this question and answer session. And you will also get some follow-up information from me on the tools you've seen today, as well as the printout or the PDF of the questions and answers that we went over here today. We hope to see you on part 2. We'll be announcing that date in the next couple of weeks. It will be in June, and we hope to see you there. So thanks again, everyone, for your time. Take care.